Hello everyone, it's been a while. I want to say the reason it took a while is because I've been doing something fulfilling and I've been off exploring the world. I found myself in Bali. I'm a new man and I now have found a new reason to live. None of that is true. I was just kind of busy. I didn't really just get around to making a video, and that's okay. Probably. I hope no one's been waiting too long. I hope no one's been waiting at all, to be honest. And so here we are, in the kind of next stage of what I want to do, which is kind of introducing dynamic analysis and using that to further analysis in general, and also touching upon the relationship between static analysis and dynamic analysis. So you may have noticed that the sound to the intro of the video was different than the previous three, and if you didn't, excellent, it's always been the same. But if you did notice, it has nothing to do with the fact that I accidentally deleted the audio file that was underlying that track, and also just can't find it again. So I'm going to call it an evolution, and as I said, I went away and I became a whole new person, and now with this new ambient track that I found entitled Deep Water Ambient or something, we're gonna enter a new phase of this channel's long and storied history, and who knows how many more evolutions we're gonna make. We're here for the long run. So one of the reasons for making this video, outside of obviously just absolutely wanting to, is I was having a conversation with someone recently relating to a very specific malware sample during some dynamic analysis. And one of the conversations we were having is around how to use the debugger properly, how to understand how it functions. And I'm aware already, like, the word debugger we haven't even used before, but I think one of the scariest things within malware analysis is the debugger and the use of the debugger. And I think taking the debugger as something that is quite scary to use and can be quite punishing and quite brutal if you're not used to it, and then saying, well, actually, if we get the fundamentals right and the foundations of what debugging actually is and how it works and how we can use the tools to best complement our analysis, then actually we can slowly begin to build an understanding of why debugging is actually by far and away, from my perspective, the most useful way to analyze malware, especially if malware is being kind of rude and is performing some anti-analysis or obfuscation, and so static analysis becomes pretty terrible. And again, I'll reiterate for the 15 millionth time, and I'll probably be doing it 15 million more times, some of the concepts and some of the terms that I'm using to some people right now don't make any sense whatsoever, and I'm aware of that. This video and all of the videos preceding this one, and hopefully preceding as well, are supposed to start at kind of ground zero. We're supposed to be talking about these concepts from a base level zero perspective. And in the previous video, when I was talking about static analysis, I didn't actually do any really. I gave some pointers as to what static analysis looks like and what Ghidra looks like, but again, we haven't really done any of the actual analysis, and that comes later. And I do think the best way to do this stuff is by doing it, and the same is going to be of this video too. I'm going to go through a debugging tool, specifically x64dbg. Others are available. I'm going to be going through that tool and outlining what the debugger is, what it can do capability wise, and why it's so popular amongst malware analysts, and the best way we can use it. So if it all sounds a little bit scary, and if debugging is something you know of but are a little bit intimidated by it, then that's fine. If you've never heard of debugging before, that's also like incredibly fine. I have like a weird, unique journey into debugging, and that it was actually the first thing I did, and then kind of learned about how to utilize static analysis, and then about the lower level programming languages that are actually higher level than that of the debugger. So I find dynamic analysis to be somewhat of a home. I quite like it. It's not nice, but it's certainly the most rewarding of all of the analysis tools from my perspective, or the analysis approaches from my perspective. So I'm super excited for this video, and hopefully by the end of it we are going to have some semblance of at least what dynamic analysis is and how we can use it to further how we do what we do. Alrighty, here I am in my dynamic analysis virtual machine. You'll notice I have two tabs, one for dynamic and one for static. I think I've touched upon this before, but if I haven't, or I've just forgotten that I have, the most important thing is that I like to have two tabs, two separate analysis machines for static and dynamic, because the dynamic analysis machine has the potential to cause some problems when it comes to sometimes derailing the machine. So sometimes, especially if I'm dynamically analyzing ransomware, which has the sole purpose of encrypting all functional systems on the operating system, if I'm statically analyzing a binary and it encrypts all of the important libraries behind my static analysis tool, then I'm going to be in trouble if I come to later analyze it and I stop the program, or it just encrypts some libraries that help me with a plugin, for example, all of that stuff. So always wise to just separate out the two. The most difficult part, as with all things, is understanding or knowing where to start, especially if I'm trying to go from base zero. And I think I've come to the conclusion that actually I can't touch upon all the principles theoretically. I can't sit there one by one and discuss registers. I can't discuss the heap and the stack. I can't do any of those things and then expect to come back and for people to actually be interested. And I said, I think on the first video I made, that when we go about doing this and when we go about kind of analyzing practically, we can't just sit around and be expected to talk and talk and talk and then do. I do believe that the best way to go about things, especially with low-level reverse engineering, is to just analyze things and just get it over with, accept that we might struggle in the beginning and that some principles may need further reading or just need further practice, but eventually it does just click. And I can speak from experience and just say it does eventually click, and I would encourage anyone who's struggling at any point during this video, or struggling in their professional careers, or even just as a hobby, it does get easier. Like, it does eventually get better, so stick with it. You're doing excellent. Let's begin. I have my main debugging tool here. I use x64 and x32 DBG for all Windows programs essentially. Now there are some exceptions. .NET binaries, for example. Again, I'm going to stop saying again, I will explain. .NET binaries, for example, using a different language, you can't debug those using x32 or x64 DBG. You have to use a tool like dnspy, and debugging comes in many different forms. Python scripts you can readily debug depending on how obfuscated they are, using Visual Studio Code. PowerShell scripts you can debug using a bunch of tools. Rust and Golang you can debug. You can actually debug them using IDAPRO if you have IDAPRO, but I think you can also debug them via x32 DBG. I may be wrong about that, but either way, you can. I'd recommend with Rust and Golang programs, you don't really need to debug those, because at the moment there aren't that many obfuscated libraries or obfuscated methods for these programs, and you can just kind of follow the money. And we'll talk about those in another video, how to kind of understand what's going on with those languages. But for now, we're very much just talking about x32 and x64 DBG as its own concept. So you'll notice, obviously, there are two. They do exactly the same thing. The only difference is one is tailored for x64 DBG, one is tailored for 32 programs. The difference between those is something that we will come on to talk about at length as we go through reverse engineering and we go through these videos. But I will just say 64-bit is double the size of 32-bit, and that kind of is a really good thing to bear in mind when understanding the differences between the two. When it comes to debugging, the most important one is going to be the registers. and you'll see eventually the differences between the two. One has registers which are double the size, and one has registers that are half the size of the other. I will give you no prizes as to which one is which. If you can hear wind, it's because there is wind where I am. So I'm going to load Darkside, which is ransomware. It was a ransomware that was fairly prolific in early 2021. It then evolved into a separate binary called Darkside 2.0, or at least analysts started calling it that, and then it morphed into another kind of binary called Black Matter, and then that went defunct as well. The history of these ransomware groups are super interesting, by the way. I have been fortunate enough to have kind of presented this research publicly, but we're not really here to talk about the history and the higher level stuff. We're actually here to talk about the lower level side of things, and I've loaded it up, but I'm going to expand it, and I'm going to do a bit of tinkering with it to make it easier to read for me. And again, I might be doing things that make it worse for you, but I can only apologize if you're learning, doing it my way. So I'm just increasing the size of things. You can increase them as much as you want. I'll be honest, I don't actually know what these last two things do. One of them's for the log and one of them's for hex edit. I don't think I've ever seen these, or I've never noticed them before, so don't worry about it. You can change the font if you want. I've never changed the font ever, but that's just because I am a follower and not a leader. I also always change the theme to dark because I was born in it. I think I just like it. I was debugging for a while with light mode. It doesn't change anything. It's just I find it easier on the eyes. So that's where we are. The hardest part with this kind of thing is understanding where to begin. And I am kind of wrestling with myself of just explaining every little thing, hoping that everyone will understand it. It will make more sense as we go through it practically. So for now, I'll just say, if there's something you don't understand and I haven't explained it, let me know, and I can either address it privately, or I can I'm going to make this a little bit bigger, or I can do it in a later video. I will probably be doing that anyway. There we go, it's a bit better. And I press cancel. I could edit this out, but again, I like including the struggles. It's kind of how my life goes. One thing I will explain readily is, don't be fooled by this bit. If you see a memory address, and this here on the left hand side, this is a memory address, and this is literally the address of where in the computer's memory we are right now. So we're at 7743F127, and if I right click and go to follow in memory map, you'll see that we're kind of at this random library called ntdll.dll. We're in the .text kind of section of that library. If you see any section, if you are ever in the debugger somewhere in the 7.7 region, you're not really where you want to be. And the reason for that is anything in the 7 region, so you see here with kernelbase.dll, nt.dll, and everything down, these are not really relevant because, well, they're just not. They're just part of the Windows operating system. They are libraries that are booted in with any software that is loaded into the Windows kind of space, and they won't tell you very much, or at the very least, they're not going to provide you any information or knowledge with what you actually want to know. What we're really interested in is darkside.exe, and we see that at the memory address 400,000, 00400,000. And why aren't we there? It's because when the debugger loads a program, it will automatically load in all the libraries, and it will start at nt.dll. There are ways that you can see every library that's loaded in and kind of jump to those libraries when they're loaded in, and you do that via preferences. Oh jeez. DLL load. You can even break when you see a DLL unload, and then thread entry, thread start. The reason that you would do this is because if the malware loads in a library of interest, or you have yourself loaded in a library of interest. And that is a technique that, oh my Jesus, sorry, my windows are going mental. If you would like to load in a malware that won't necessarily load in itself, like a DLL, for example, and that's a technique that we will talk about at some point in another video, you will want to tick these because they allow you to see when a library has been loaded in, and that's pretty cool. So in order to go to where we want to go, we actually just we go to run. Now run, usually when you press it, will run up to a certain point. Which point? Well, you can decide which point. You can, for example, put it what's called a breakpoint. Now a breakpoint, there are several types. The most common is called a software breakpoint. I just want us to call that a breakpoint because it causes some confusion. A breakpoint is essentially you click this, or there is a hotkey for it, which I think is F2, but you can set one. I swear it's F2. Yeah, it is F2. So if you click F2, it will set a breakpoint for you. So if I just do that now, oh, did that do anything? Yeah, there you go. It just sets a breakpoint, and what that does is I can execute, and it will jump to that area of memory, and it won't. It's not a case of it jumping there because that's where you told it to jump. It's just following the natural order of things, and you've happened to set a breakpoint on where the malware is, or the EIP, or the what does EIP stand for? Pointer, something pointer, EI pointer. Someone will correct me and put it in the thing. My memory is going blank right now. But either way, it basically it follows the natural order of things, and it breaks on where the pointer is naturally going anyway. Now this is really useful if you want to put a pointer somewhere where you think the malware is going to jump to, or somewhere that you just want to skip a loop, for example, because when in the debugger, the loop will just go on and on and on and on until, well, it's ready. And we'll see that. I will go through a practical example in a little second, or when the section is over. But breakpoints, super useful. In fact, they are mandatory for doing dynamic analysis. You will need them every time you debug, and it's just a useful thing to know. So without the debugger, without the breakpoint, I think it's disabled, I'm just going to run, and it will take me to, I'm now in Darkside, and I know that because, well, I know that because I can see some functions that are just called Darkside, so that's a good sign. But also, if I'm ever lost, if I just follow in memory map, I'm somewhere in Darkside.exe, and these, you can see the blue is kind of the sections of the program you're looking at. So before we were here, and now we are here. So we're on the right place now. What I'm going to do right now is I'm going to take a snapshot. And the reason I take a snapshot is because I'm wary that things are going to go quite wrong. And if they go wrong, I am going to need to revert back to a place that I was before. And we've talked about snapshots in the past, but this is the main way you're going to be using them with dynamic analysis. So I'm just going to go Darkside before execution. And what I'm going to do, like a crazy person, is I am going to, it's going to have a little fit because I haven't put enough memory inside my virtual machine, so it's going to take a little bit of time to understand what's going on. So in the meantime, I might actually just explain some of the things that are going on the right bottom hand side. So here on the right hand side we have our registers. Now these are registers, these are places in kind of small areas of memory, tiny areas of memory that can store values. They are used by programs in order to essentially move, add, subtract, hold, pass variables into functions, store values essentially that can be used by different things and different operations. They are tiny, and because they're tiny because they're meant to be used very quickly, they're meant to be changed very regularly, and the values can be stored either on the stack or the heap, or they can be stored in a more permanent area of memory, and that's done through different function calls. That's done through different operations. By operations, I literally mean by push or move or XOR. But for the most part, it's done by Windows APIs, memset or heap alloc or string copy. There are a few that you can use to basically take what's here and put it in here. It's all take what's here and put it in here. It's also possible for registers to hold values that are what's called pointers. Pointers are literally values that point to another value. So for example, let's see, so that's, you can see here ECX refers to the Darkside.entry point. Well, what is that? Well, if I go to follow it in disassembler, we're actually there. We're actually there already. 40, I'm going blind. 40B 2BD is the same here. I might actually just increase the size of these just a little second, because they're making me go a bit. Registers 10. There we go. That's a. Oh my. Registers 10. Save. That's a bit better. We can see that ECX points to a memory address. Now that looks all fine here, but here, wait. Yeah, that makes sense. Okay. So this points to this here, but if we actually look at the underlying code, we're already here. You can see 6A106810, which is not here. That's not that, but that is here. Now what this is the literal hex bytes, which hex bytes make up the foundation of the assembly language. So all of this here, this is the underlying code. This is all of this here. So you can see this here ends in 00FF1500 C440000 FF1500 C0 4000. Now you could, if you want to, learn all the hex codes and what they mean, so that you would never have to look at this ever again. But I would really recommend just taking the time to appreciate what you're looking at, and understanding what it means relative to this, because this is the nicest it's ever going to get. This right here is the nicest the debugger is ever going to look. So with that, we now have kind of a bunch of instructions. We've got a push, we've got a push again, and another push. Now, interestingly, the push function is what it's going to do is it's going to take this address here and it's going to push it on to here, which is the stack. Can I increase the stack size? I can a little bit. Let's make it 10 as well. The stack is also a place where areas of memory or values can be stored. They are it's put on what's called a first in, last in, first out policy, LIFO, which is essentially, again, the best analogy that's used, and I'll probably have an image on the screen, is what's called like stacking plates, i.e. when you put a plate down, you put 5 plates down, the plate at the bottom, you cannot access it without taking out all the other plates first. So last in, first out policy means the register that you, or the value that you put at the top, is the one that you have to use first in order to get to the others. And that is a fundamental principle that sounds a lot more challenging to understand than it actually is. And you'll see when we look at functions in the debugger, you'll see where the values are placed on the stack and how they're purposefully placed in order to then be used in a function or be used at another point. It will all make sense as we do more. And with that, I'm actually not going to pause, but what we're going to do is we're going to look at this alongside static analysis. And the reason we're doing that is because you should never debug alone. Never ever debug. Well, you should, for the most part, never debug without looking at the static analysis as well. And the reason you shouldn't do that is because you're actually just making your life a lot worse for yourself. You're making it a lot harder. And what you can do and this is how we're going to be conducting the rest of these videos, is we're going to be using the debugger alongside static analysis to try and understand what's going on. So I may have made things a bit more complicated by doing this section first, but nevertheless, what you're looking at is as hard as it's going to get. The fundamental principles of this video will carry you forward for the rest of all of the other videos we're going to make that is going to interweave static and dynamic analysis. So without further ado, let's bring up the static analysis kind of machine. We'll load in the Darkside binary into our Ghidra, and we're going to look at them side by side, and hopefully we're going to have a bit of an understanding of how this all comes together. Alrighty, we are going to press on and go ahead and do some very basic static and dynamic analysis side by side together. I realize I'm about to do something that I pretty much at the beginning of this video outlined what not to do, which is I have Ghidra in the same window as my debugger. The reason I've done that is literally because I cannot find, at the moment, not that I've looked very hard, a decent recording feature that allows me to kind of switch between tabs. So I am doing this for the purposes of making my life easier. If you can, or rather, not if you can, please do not follow this example. Very much a jackass, don't try this at home kind of thing. Please use 2 tabs instead of 1, and keep Ghidra in one and keep your debugger in the other. Ghidra was at the time debugging. This is Ghidra, and we'll be going through it in a little bit. Now, one of the things that Ghidra doesn't do that IDA Pro does really well is it takes you exactly to where you want to be. You can see right now, like, Ghidra has put us literally at the beginning of the malware. 400 is the, or 400,000 is the memory address of where the malware starts. So if we actually just go to that here, we can see that that's exactly where it is. If we go to that in the disassembler, you'll see the actual the instructions are exactly the same. 4D5A 90 00030. Now 4D5A, for those of you playing at home, if you see 4D5A, you know that it's an it's an executable, basically. 4D5A in non-hex, in ASCII. Sorry, I'm in the wrong place. Here. What? Okay, that's wrong. There you go. 4D5A is MZ. If you see this is kind of the sign that this is an executable, or a DLL for that matter. We can talk about the kind of executable, or rather the Windows software headers at some point, because they all have kind of some kind of meaning and have function and purpose. But we're not here to talk about that. My point is that the Ghidra window is not helpful, because whilst in the debugger we are right here, we're exactly where we want to be. In Ghidra we aren't, and this is one of the advantages of having the debuggers side by side with you, is I can readily copy this memory address. So in the hotkey for it in XDBG is Alt-Ins. If your keyboard is funny or kind of weird, you can actually change it via hotkeys. So I've changed it to Alt-Delete because my insert key on my machine is a bit broken, so I've changed it to make it just more functionally easier for me. You can change it to whatever you want as long as it doesn't clash with any of the normal hotkeys. And what that will do is it will save the address here, and save the address that your EIP, extended instruction pointer, is kind of pointing at. So if you're here and you're trying to copy that, that's not going to work. You're going to end up copying that address. So make sure you're, like, the highlighted line is the one you're trying to copy. So once I've copied it, I can actually just go to Ghidra, and I'm using my own hotkeys. I've literally made hotkeys for Ghidra that replicate or mimic IDA's. The reason I've done that is because Ghidra's hotkeys native are tragically bad. They are so unintuitive, and sometimes they aren't even hotkeys. They are just right click, find the thing you want in a long list, of which if you haven't really reverse engineered before, you're not really sure what you're looking at. Useless. So I can only recommend going to my GitHub. I'll post a link down below. There are other people who have done hotkeys as well, and they've done a super good job of it. So anyone who is doing like a hotkey script for Ghidra, please use it, because if it's anything like I did, it'll be much more intuitive and much easier to use. I will also say that I have like a custom dark mode on Ghidra, and that's because when I was installing Ghidra way back when, it didn't have a dark mode. Ghidra, I want to say we're in 2.11, version 2.11, that has native dark mode. And I'm not sure how good it looks because I haven't used it, but I'm sure it's much nicer and much easier to kind of create than what I've had to do. So if you like dark mode, please go and download it, the new native Ghidra binary off of GitHub. I'll post a link to that as well. Anyway, let's begin. So I've copied the address and it will go straight to it. And we can see we kind of have a similar thing to what we have in the debugger, i.e. we have 3 functions and then an exit process. Now the difference is that Ghidra, as a decompiling static analysis tool, it takes the assembly, and the assembly is the exact same actually. So if we just look at the hex bytes before we look at any of this, 6A10, 6810104200, 6A10, 6810104200. It's the exact same. The only difference is that Ghidra's function, its main purpose, is to take all of this data and present to you what the actual C equivalent code is supposed to look like. So it will read all of the assembly instructions and then it will go, okay, this is kind of what I think it's doing. And this is really useful because it provides us a much more readable format than this and this. And this is why the debugger is limited and why you shouldn't just be using it on its own, because I can tell what's going on here, but if I am strapped for time or I just care about the way my life and time efficiency, I cannot just continuously use the debugger unless you really want to. Just the debugger on its own. I would always recommend having both. So I know that Ghidra, or rather the Darkside malware, is going to have 3 functions. The first function is going to take in 3 variables. It's called it dat blah blah blah, dat blah blah blah, and the ampersand just shows it's a pointer to something. The bracketed type, please don't worry about this, and if the NSA is watching this, which I hope they are, please add a native hotkey that, like IDA does, to remove types. This is really annoying. It like clutters up so much and it makes it look a lot more complicated than it is. Essentially what's happening is Ghidra is recognized as a function and that there are 3 things to be passed into it. And we can do that too. We can look at the debugger and say, okay, I've got 3 things being pushed. They're being pushed onto the stack and therefore they have to be used at some point. And we know we can see a call coming up, so we know they're going to be pushed into that function. And because we're following the principles of LIFO, we know that 10 is going to be put on the stack first. Then whatever this is a, let's see, it's, okay, so it's a load of data basically. And then it's only 10 bytes. And the reason I can say it's only 10 bytes is because I can see 421010, but then the next function is 421000. So the difference between this and this is 10. So just bear in mind where we are. We're at 421010. If I go to 421000, we're actually, you can see the hex editor just stepped up 1 line. So this is cool. This is only 10 bytes long. So I was wrong the other way around. It's the other way around. This is only 10 bytes long. Again, we know that because this data set starts here, and this one starts at 000. So this bit here is only 10 bytes. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have to have a look and just double check that. But on the surface, that's exactly what it is. Oh, no, it isn't. It's a whole line of bytes. Sorry. It's not the number of bytes, it's the line. So if 10 in hex, let me just quickly get up. Sorry, it's in hex bytes. So if I just do a calculator and I go to programmer, and I do hex 10, it's going to be 16 decimal, and there are 16 bytes in a row. It's just the way you remember it. So the top row is that, there, 16 bytes. You can tell I'm doing this live because I'm figuring it out on my own. But the point I was saying is that we can work out, because of the way the stack works in the LIFO kind of data structure format, and because we are good at maths with a calculator, we know that what's going to happen is this function is going to take in 3 variables, and just kind of pop 1, pop 2, pop 3. And because it's last in, first out, it has to use this one first. Or rather, this is the one that's passed in first, then this one, then this one. And Ghidra does recognize that as well. The type, please just ignore anything with like int star or int or character. It doesn't really help. Ghidra is just trying to interpret the data that it's seeing, and is readily just trying to tell you, okay, I think this is a pointer to an integer variable, but this is just an integer. The ampersand is a pointer, and this, if you combine a star with a pointer, it's a dereference pointer. So it's saying, okay, the memory that's here is actually a value, whereas this is just a straight up pointer. And then we have 0x10. I'm actually gonna change the font color because that is nasty. Decompiler display, color for constant. I'm gonna change it to bright yellow. Let's see how that goes. That's fine. Yeah, that's perfect. Okay. So similar to the debugger, we are basically just more readily able to see what's going on. Now, we already said that this is probably, this is the smaller data here. Like, it's only going to be 16 bytes. So I'm going to call this small data. And then this is going to be large data, I think. Let's just call it that. And then if it doesn't work out, I'll deal with that in a little bit. Let's have a look. Or is it the other way around? I bet you it's the other way around, isn't it? Ugh. It would make sense that this is the smaller data. Yeah, it is. Okay. I'm silly. So this is small data. And the reason this is important is, before I do anything else, it's really important to label up as much as possible, because maybe this function isn't as helpful, but you'll see in larger functions where you have a bunch of variables going around and round, you want to be able to make sure that they're labeled up so you can kind of create an idea for yourself of what's going on. And sometimes it may be that you actually aren't able to readily work out what's going on without labeling up or without using the debugger, because static analysis can be quite punishing. And we will see that as we step through some of these functions. I can tell already. We all know I'm doing this live, so I have no idea what this malware does, except for encrypt. But we all know at some point there's going to be a function that just looks really nasty, and we're going to have to work out what it does. Initially, it will look bad. The more we label things up, the better it's going to get. So, small data. And then, large data. Large data. Nice. And then 0x10. And one of the neat things you can do... Oh, I'm going to cough. Am I going to cough? No, we're all good. One of the neat things you can do... Oh, here it comes. One of the neat things you can do is you can use these and continue to label up as you step through functions. So this has not been useful in and of itself. I've labeled up some stuff and I go, okay, why do I care? Well, if I step into this function, it's pretty nasty. I mean, it could be worse, but like, it's pretty grim. It says here at the top, exactly the same as we've seen before. Int param1, param2, and param3. Well, we know what these are because we've done it in the previous function. So param1 is small data, param2 is large data, and param3 is 0x10. So if I literally just blanked on what I've written. I'm going to call that small data and pray that that is correct. Large data. And then one of the quick wins actually that Ghidra has that IDA does not have. In IDA you cannot label things as an integer or anything that starts with an integer. So if I wanted to do 0x10 in Ghidra, I can, which by the way is uint16. So I can just call it 16 if I want to. In IDA I couldn't. In IDA I would have to say 16, which is dumb. Why is that the case? I hate that. Bruh. There you go. Thank you. Okay, so I realize I've done not all that much analyzing with the debugger just yet, but we'll get there. I'm trying to emphasize that the debugger should be used when you're stuck on static analysis and when you can't get any further or you're unsure. And I will always say is like the golden rule. If you want to make a statement about something, whether you're working on maybe an instant response case or you're doing something professionally, and whether maybe you're developing some red team tools and you want to make sure that you are that the thing that you're saying your malware does the thing. I'd never use static analysis to make that claim. I would always use the debugger to kind of verify and check that the thing is doing what it's supposed to be doing. And obviously everyone at a high level program language debugs all their code, and that's because if they don't, it doesn't work. From literally the other end of the spectrum, from the malware analysis side of things, you have to always be checking, because if you're writing a report on a malware or you're trying to teach someone about malware analysis, the static analysis will only tell you half the story if you're not fully experienced and not fully aware of what's going on in the static analysis decompiling tool. I would always verify if you're unsure with the debugger. So at the moment we're fine, but it may be in a little bit I might need to refer to the debugger to understand what's going on, and I think that time is coming up right now. This is not going to be a reverse engineering video in terms of, we're not going to be reversing Darkside today. We'll probably do that in another video. I wanted to just kind of use this point of the video to just emphasize how important the debugger can be. And as I said, I think we're about to hit that point because I can see what looks like a loop. And I can tell that, because of several reasons. Number one is I can see a while statement and an if statement. And if and while loops, again, if you're not familiar with if and while loops, all I can say is the best way to get really good at reverse engineering quick is to do a programming language. Python, C++ if you're feeling really brave, but like just understanding the fundamentals of programming, understanding how programs work and operate, you are well on your way to kind of getting a head start on someone like me who basically approached reverse engineering from ground zero with like, I don't know what a computer is, I'm just here for vibes. I would really recommend just understanding ifs, whiles, fors, especially with C and C++. There are a number of intricacies that it has that Python and higher level languages don't have, and because the decompiler is written in C or it's written to translate to C, you'll be way on your way to winning if you do some basic C first, or some Python, or anything that gets you familiar with programming languages. There is a really good book that I have not read that I saw on Twitter as a recommendation. I will post it in the link. I've heard only good things about it. It is quite low level, and it's related to assembly and C and the relationship between the two. But if you want to read it for a bit of holiday reading, or just because you like to hate yourself, I'd recommend it. I'll post a link in the description below. But I'm probably about to switch to the debugger in a little second. There are just some things that are catching my eye here. I can see a pointer, like the block 0 of small data is being passed into a variable, its own variable. And what does that look like in the debugger? Well, let's have a look. So I can, what have I done? I think I still have the function. I do. That's one of the things about Ghidra. If you accidentally click on the wrong thing, you can be punished for it quite readily because it doesn't take you immediately back to where you want to be. So let's see. I am here. And what does that look like? So it takes basically EBP, so the base pointer plus small data into EAX. And what all that means is EAX is now going to have the address of EBP. I'll show you that in a little second, just to prove it. And then it's going to take the first 4 bytes of that function, put it in EBX. It's going to take the next 4 bytes and put it in EDI. It's then going to take the next 4 bytes and put it in EAX. That's interesting. So I do want to see what that's doing, just because I'm curious about it. I don't know how much it helps or what it's used for. But we can see it being referred to later on and stored as what looks to be a that's interesting, as a memory address. We'll find out. We're definitely going to find out. That's going to be one of the missions from the debugger. It's a do while loop as well, which means that this is done until whilst this is true. And then there's another do while loop. While true. Yeah, I haven't seen large data being used yet. I can see it there, but I just want to highlight it to see if there's any other uses of it. Again, these data pointers make this much more messy than it needs to be. Ignore all of that. Like, ignore all of it. uvar7 plus large data plus uvar9, which is 0. It's actually, it's a counter. So if I relabel this, and I say it's a counter because it's going to increment by 1 every loop. You can see that counter equals counter plus 1. So that means large data, or the pointer to large data plus counter. So large data, first byte, second byte, third byte, and so on. And then whatever you are. What are you? I don't know. Do you tell me at any point? Okay, it's unknown. So this is loaded at runtime, which means that I'm not going to know what this data is at during static analysis. During static analysis, without dynamic analysis. Sorry, my brain just scrambled there. Without dynamic analysis, I won't know what this structure is or what is at this location. But uvar7. Okay. And then. uvar3 is. Okay, so that's a counter as well in its own way. Yeah, interesting. It's adding, and then it's returning. Sorry, I'm doing this in my head now. Okay, cool. I think I roughly know what's going on, but we're going to use the debugger to confirm. So we're going to step over, and we can see 10, 4211010, 42100 is being added to the stack, which is ideal. It's what we want. So with that, we're then going to step into. The difference between step over and step into is if I'm stepping over something, I'm not stepping into it. If I'm stepping into it, I'm literally going into the function. So we should see when I step in, and you can use hotkeys as well. F7 for stepping into, F8 for stepping over. If I do this, then we will be exactly where this is here. So you have what's called a function prologue, and all that is 558BE. See, all the function prologue is just the stack writing itself and the base pointer writing itself. So I know what I've just said makes no sense, but it will make sense again when we look into it in more detail and understand assembly at a more fundamental level. But for now, we have 558BEC, which is going to be the function prologue, and then 5351, 52, 56, 57, which is just going to be, again, that you see it there, is just pushing all of the registers onto the stack to then save those addresses, so that if the malware needs them, or rather if the function, I should say, needs them, then they can just repurpose them at another point. So then we move f dot, literally the value 0xFO into ECX. So I'm actually probably not going to go back to, I will probably go back to the static to Ghidra in a little bit, but so we see currently what's in ECX is the entry point to, so that is literally the entry point of where we were before. But now if I click over that, what's happened is FO, which is just a value, has been moved into ECX. What does it mean? At the moment, not very much. And then it's going to move whatever this is into into ESI. So what are you? Oh, okay, that's this thing here that we were referring to before. So we'll find out exactly what this is in just a second. So what are you? It's empty memory. So it hasn't been declared yet. It's just empty memory. And it's going to be filled at some point. You can see it here. Like var 7, which is 0, but then so we're going to find out effectively what this is. It adds a okay. I think actually what's going to be happening is this empty memory is going to be, it's going to take all that the large data block, and it's going to move it here after decoding it. We're going to have to wait and see. We're going to be down here, so we'll just wait and see. So at the moment all we've done is move a 0xFO into ECX, which is a register, and we have moved this block of data starting at this memory address into ESI. That's all we've done. What's about to happen now is EBP plus 8 is going to be moved into EAX, and all that means is EBP, which is the base pointer. If I follow it, let's follow it in dump 2, which is the, I think, which is the opening function of the malware, if you remember correctly, for OB 2BD. And if you remember this is this. Let me just go back a second. This is this. 6A, 42, 6A10. I'm going really slowly because I want this to come across as well as possible. The debugger is essentially just an extended arm there to help you if you are in any way confused about what you're seeing. So all that's happening right now is we're going to be moving EBP plus 8. So though the base pointer has 19FF60, which is in and of itself is a pointer to this address here, and where is a pointer to here, that's not really what it's actually doing. What you want to look at is this little window here between the kind of not decompiled, but the assembly code and the hex bytes. This little window here is such a godsend, and I use it. Well, I obviously use it all the time, but it's one of those things that I always look for to check when I'm doing something. So, and it can be really useful if you're looking at more complicated malware that is either broken or purposefully has anti-analysis techniques. This will be, as we move into future videos and future content, one of the most fundamental windows in our in the debugger. It's just so useful because what it shows is it kind of removes all the guff with pointers and having to translate addresses. It says, okay, EBP plus 8 is actually this address here. It's going to point to 0019FF68, which makes sense because EBP on its own is 19FF60. So EBP, so that plus 8 is 68. Makes sense. However, it's a pointer. What it's actually pointing to is this address here. And what we can do is follow in dump value instead of address. Value. You can also do it here too. You can go follow in dump value. and you're going to end up at the smaller function, the smaller of the 16 byte. We called it smaller data in Ghidra. And if you don't believe me, well, that's a problem. I think if you relabel it, it has a no. It's fine. 421000. I admit that isn't as easy to read as I thought it was, but we are there. So 421000. So what it's doing is it's moving into EAX. The entry point, or rather the first, it's moving in. You'll see. It's just easier to explain that way. So EAX is now here. It's now exactly here, and Ghidra does that too. Ghidra says that is what happens as well. It puts IBV-file6, which is EAX, but don't call it EAX because EAX is just a temporary register where it puts the data. It puts the small data or the pointer to into IBV-file6. Now we can label this up too, so we can just call that pointer small. I like camel case. Which is instead of like it's not good practice, but I am malpractice, so get used to it. So that's points to small data. Now this is going to be the first 4 bytes, this is going to be the second 4 bytes, and this is going to be the third 4 bytes, and that makes sense. So this is actually, sorry, computer speak, this is wrong. This is the first 4 bytes. So actually, let's not call it pointer. Let's call it first 4 bytes. I know I've just said I like camel case, but I am chaos. Small. How's that? How's that? This is second 4 bytes. Small data. And yeah, I wonder what's coming up now. I'm going to copy it so I don't have to type this out every time. Ah, come on, dude. Third, 4th, small bytes. Oh, I've just done the thing I said I wasn't going to. Nice. So, now this makes a little bit more sense, although it might not if you're looking at it for the first time. All that's happening is these first 16 bytes, so small data, is literally a chunk of 4 memory addresses. So it's going to be using, their values, sorry. It's 4 values, not addresses, 4 values. And all of these values are going to be placed in memory, effectively. And the 0xFO is basically a way to delineate where to put it. And we'll see that again in just a little second. So what we'll see is these registers filling up with bytes. So EDX, EBX, EDI, and EAX. And we'll see that here. So move EDX. So you can see that EDX has just been filled with the first 4 bytes. So that's these 4 here. ED, F9, E5, ED. ED, E5, F9, ED. And then EDI is going to have the same. It's going to have the second 4 bytes, which should be 86FO FD53. And you can see XTBG has a really nice way of highlighting the register that's just been used. 0040B2BD. And then, boop. I think I just lied about that, by the way. I don't think that does. EDI has the third 4 bytes. So AB185838. Yep. What? Oh, okay. Oh, one thing we need to address right now. It's called endianness. Endianness, basically, without getting too much into it, is everything you read here is backwards. I just can't be bothered to explain why that is. I'll do it at another point. But effectively, you'll see here, what you want to see is AB185838, but actually what you're seeing is 385818AB, because it's doing it backwards. It's going like this. It reads all the data that way. So One thing to be really careful of, if you're expecting to see something, or you're writing a report about some variables or some memory, make sure that you are cognizant of the little endianness of the values. That can be really important if you're trying to decipher a key, or you're trying to decrypt some memory using a static tool like CyberChef, or a dynamic tool like CyberChef, and you have to enter in some value. Just make sure you're entering the key in the right way, especially if it's like an XOR key or something with hex related to the data that you're seeing in memory. And then EEX is going to have these last 4 bytes, DF, D9, 6B, 64. And there you go. So that's all that's happening here. And then what it's going to do is it's going to take, as Ghidra says here, it's going to take these values and it's going to put them somewhere in memory. And the reason it says IVFAR3 as in 0, so I might just label this up as well. FO, is that going to let me do it? It will. So the reason why it says that is because at the moment ECX is in FO is, or F0 I should say, is in ECX. Well, ESI plus ECX plus C, which is 12 in decimal. If you don't believe me, there you go. It's taking the third, so it's taking the 12th byte of this area of memory. So if we go to this here, actually it will be empty, but if we just run through this, you'll see, okay, it's taking what's in EDX and putting it there. Then it's going to take EX and it's going to put it there. It's going to put it 4 bytes before because ECX plus 8 is 4 bytes less than C. So if I scroll up, you should see it here. Cool. And then it would be 4 bytes here, which would be the next 4 bytes, and then 4 bytes here. So actually what it's doing, it's reversing. All it's doing is kind of reversing the key and then cleansing the memory address. Now, if I was a malware analyst, I would say this is a really good signature, i.e. this is fairly specific. It had these things in register. It has these assigned values in a register, and then it's going to cleanse the data with 1010101010. I'm pretty sure if we were to write a signature, or a Yara signature as it's called, Yara is a tool that malware analysts use to kind of signature malware, then pretty sure we would get something for this. Now this is a pretty old malware, so I'm not going to do that, but an interesting choice by the person who made this malware to cleanse the registers. It's literally subtract the register with this value. So you'll see EDX, just pay attention to it, is being cleansed a specific amount. It's a fairly specific amount actually, and then ECX being subtracted by E. I wonder if that's going to be playing a part in something else to come. Okay, I was actually wrong. So what's going to happen, or what is happening, is it's actually not. I thought it was going to subtract the data to the point that it was like nullified and it was a random data. I would still say this is a signature because it's asking the. You'll see in a second. It's basically going to the data that is this many bytes fewer than before. Again, I know I'm making a little less sense than I was about 5 minutes ago, but you'll see what I mean. Because what's in EAX right now is what was in there before minus 10 10101010, and then it's going to put it somewhere in memory. Where is this? So you see it's basically creating a weird structure here. So, and it's going to do it, ECX has to be 10, and because it's subtract jump if NS, jump short if not sign. Interesting. I'll be honest, I'll know what that means eventually. So you'll see it's creating like a kind of set of values. This is junk data. Like, I'm not expecting me to understand what it's doing just yet. But this is one really good thing about the debugger. And one good thing about breakpoints that we haven't talked about is I don't need to step over this and wait for it to do its thing. I know exactly kind of where the data is going, and that's all that really matters for now. So what I'm going to do is I'm going to set a breakpoint here, and I'm going to execute the malware, because I know the malware can't go anywhere except for here when it's done. So if I execute, we have a load of data now that wasn't there before. And then it's going to XOR. When you see XORing of the same register, that means it turns it to 0, because if you XOR something by itself, it equals 0. So you'll see EDX turn to 0, and then ECX also turns 0. So we've done this loop here, effectively. Okay, yeah, that makes sense. So the loop continues until FO is effectively nullified, and that happens because 0x10 is removed from it every loop iteration. So if we do F0 is 240 minus divided by 10, because it's minusing 10 every time, is 24. So there'll be 24 loops of that function, 24 loops of this loop, because eventually when it doesn't equal anything, it will nope out. So we have 24 iterations of this, which again, one of the great things about static and dynamic doing it together. Now we can label this up here, we can label it up here, or we can label it in Ghidra. I would recommend doing both, and it's a great time for us to introduce labels. So semicolon, and I'm going to type in loop equals 24 times, and then put it there. So then that's there, and you can also do it here as well. It's the same hotkey as far as I'm concerned. It might be different because I've got some funky hotkeys going on. Loop equals 24 times. And this is just really useful for when you come back to just know what's going on. You can't save databases in... actually, no, you can. But it's more common to save static databases. So if you want to pass this over to another analyst or just a friend, then you can do it like that. And that's, again, I will continuously highlight the usefulness between going back and forth between the static decompiler tool and the debugger. So my computer decided to break on me, which is a very annoying thing. So I've reset the virtual machine because I took a snapshot, so it's not the end of the world. And I'm actually going to show you a cheat. Usually the main function is called entry or main. So if you look for either of those, you should just end up exactly back where you want to be, instead of doing the technique that I was talking about before, which I actually prefer, by the way, of finding the value of where you want using the alt-ins or whatever hotkey you've used. So I actually will need to redo it again because there we go, copy, change, alt-delete, which is just a nicer way for me to do it in this instance, and then we can alt-delete and go to where we need to. And actually, weirdly, it's a kind of a blessing in disguise, because one of the things that I actually forgot about with Ghidra, and as I was watching back the footage that I had managed to keep, I remembered, like, oh, damn, that's an annoying thing that I didn't remember, is that Ghidra, sorry, I'm trying to do two things at once. Ghidra will... It's really tempting to label everything up as much as you want, and I was really pushing for it, and I would still say you should do it, especially if you're only paying attention to the decompiler, because well, the decompiler is really good, and it's a really nice way of reading the assembly. However, because I am trying to encourage, and I would actively encourage that everyone tries to follow this method, at least when you're just starting out, in order to understand assembly. Once you understand assembly, whatever, who cares? But when you're starting out and really trying to understand assembly from a dynamic and static point of view, it's one of the things Ghidra is really limited at is it will label variables as the register that they are representing. So we were labeling up this up before, and we were being really cocky about it, saying, okay, well, this is going to be x0xfo, which is 240 in decimal. So naturally I'd be like, okay, well, 240. The problem, if you are paying attention to the left-hand side, is that it's just changed a register into the value of 240. Now that's a huge problem, because registers are static. Registers don't change. The value inside them changes, but the actual register doesn't. So Ghidra, and I actually went to look this up in between my machine breaking and being here. It's actually a feature. It's not a bug. It is a feature, and I do wonder if it's been changed in the newest Ghidra. I very much doubt it, but it's one of the weaknesses of Ghidra. If you are trying to pay attention to the assembly, you got to be real careful with what you're labeling up. Now, what you do have is you have the debugger to tell you what the address is, but if you're just starting out reverse engineering, labeling up registers is the last thing you want, because you'll be referring back to the debugger and you'll be saying, where am I? What is going on here? Why is ECX called 0xfo? That is one of the big drawbacks, and to be honest, one of the big reasons we need the debugger, because it allows us to focus on registers. It allows us to kind of focus on what's going on. And I didn't want this video to just be a reverse engineering of Darkside. We will do that at another point. I am trying to overtly state and show how useful the debugger can be, and how useful dynamic analysis can be when working with Ghidra, when working with static analysis tooling, because it can help explain what's going on. And we can use comments, as we were saying before, we can use comments to work out what's going on. So loop 24 times, and then we can make that a better color at some point just to make it pop a bit more. So we've got that going, and then there'll be a load of data that we are going to use, and it involves the larger block. Now, labeling up these is fine, like labeling up this kind of stuff is fine. So this is, it was empty mem, but I'm pretty sure that's where the new obfuscated code is. And the reason I say that is because if I go to this, so we've done the loop, right? We can set a breakpoint. We've done the loop, and in theory, once we do this loop, we can actually set another snapshot, and then we don't ever have to do this bit again. But we know that there's a big loop coming up involving. Ow! Sorry, my window is having a fit. We know there's a big loop involving. You can see. This is the instruction that I'm just at Ghidra in the assembly bit, because you can see it moves the AL, so like 1 byte with ECX plus new obfuscated code, and that is that 401050, which is here. So if I follow that in assembly, that's BB27. It's the beginning of the newly created what was small data. It's basically what this loop has created, is where all of this is stored in. So it takes that, so it moves into AL, but as we were kind of touching upon before, I'm not even sure if the recording saved properly. I bet you we didn't. It takes the value and adds it to AL. So whatever was in EAX before, which where's the last mention of EAX? Here. Yeah, I can't see any other mention to EAX. So EAX will contain that value, but it now contains a new value, and it's not a memory address. It's just a pure value. So it's going to take that, it's then going to add something to DL, whatever's in DL. Or rather, yeah, so whatever's in ESI plus EBX, which is 92B2. And if you remember correctly, 92B2 is the larger data. So again, Ghidra has made like a very confusing way of saying add the first byte of this new data that we have, add it to the first byte of the obfuscated, large data, which is this. So let's label that up. I can't spell. I'm using camel case now. And what? Ghidra's done a weird thing with the line. Is it any better if I move? No, it isn't. Wait, never mind. Basically, ignore everything else. It's just large data plus new obfuscated code. And the uvar9 is the count. I'm going to get in trouble if I label it, but just know it's count. Yeah, really annoying. So for now, just it's count plus the also count. But bear in mind that this might not be a register, so we might be okay here. Please. Where are you referred? Let's just have a look. Oh, never mind. Yeah, unfortunately, it is a register. But as I said, if you're ignoring the assembly, then and you just want to pay attention to the disassembly, the actual like C compiled code-ish in bunny quotes, then you're okay. So all UV-fast6 is byte large data. I should really byte plus new data look byte. So that's all that is, and I could in theory like take a screen grab of that and use that for something, for like, I don't know, some fancy open source blog that I would be writing. And yeah, I can now, let's see, I can now revert it back because it might be neater from an assembly perspective. So I'm just going to go back 3 times. Yeah, so we know roughly what's going on here, and that's all thanks to the debugger, by the way. I could have done it through Ghidra eventually, but it's much quicker with static analysis. So we're just going to add those two together, and it's going to end up in the DL register, because on the left hand side it's always right to left, so the value will be added to DL rather than DL be added to AL. So it'll go here, and it's 4D. And why is it 4D and not the whole value? That's because it's AL. So if we take what AL was, you can see it here, and this is why I love this window. AL is BB and DL is now 4D, but if we do BB minus 4D, we will end up with 92, which is what the value was in DL before. So then what happens? Well, it moves, then what does it do? It moves UV-fast7 of that, which should also be 0. Interesting. That's interesting, because it should be... Oh, it moves into AH, sorry, yeah. That's weird, it shouldn't... Oh, now I'm confused myself. Why is it 4.9? Bruh. Oh, EDX, not ECX. Sorry, it's because the registers are different. EDX, not ECX. So it takes the value of EDX plus the base count. Okay, so ECX plus 410050 is the base, because currently ECX has nothing in it. However, EDX on its own is equal to 4D, which in calc speak, or rather in calc speak, in hex is, let's do the maths, for D, it's 77. So we are 77 bytes away from the base. Just trust me on the maths, that is correct. I could calculate it, but I haven't. So we're at 77 bytes away from 1410050. And then that byte is moved into it. So what I'm explaining in very minute detail, but essentially what's happening is there is a algorithm to decrypt a load of data here. And that will eventually pump out some code. Now, I'm not sure what that is going to be, but we can work that out eventually through stepping through the data and continuously following what is added to which register, what is added to what, and then what result is kind of produced at the end. Now, one of the great things you can do is usually with a function like this, I kind of know what's going to be returned, because we've got this big loop and there's a load of decryption going on, and then that's it. There's nothing, it's not being used for anything. So I can only assess that before actually analyzing it, that there is going to be a load of decryption going on here. It's going to pump it out, and then we're going to end up with some kind of value. Now, where does it get pumped out to? It's gonna get, I think it gets kind of added back to it gets basically added back to here, and the original kind of block, or the newly created block, is going to get a further alteration. And the reason I say that is because AL is moved into EDX, so it's moved into this byte here, but AH, which is the new byte that we've just seen, the 49, is being moved back into the original base pointer, like east. I'll just move this to this dump here, because there are 5 available. And then it's going to do a comparison that basically compare if EBX is EDI, and if not, then yeah, so it's going to do it 10 times, because it increments EBX at each point, and then EDI is 10, so it's going to do a comparison, and eventually EBX will equal 10 after 10 loops. So you can see 49 has just been added to where BB was before, and then we go again, so we should see 2C, and then 08, and then eventually we're going to end up, eventually these arrows here represent when it's dark, the arrow will not take the jump, whereas if it's light, it will take the jump. I can show you what that is by choosing something. Okay, never mind. Eventually we'll get there. It will look like that, and you can see it's a slightly lighter color now. In light mode for the debugger, it looks a lot nicer than this. And that's effectively what's happening. It's kind of taking these bytes and putting them here. Now, the malware isn't done, because there is a second loop here. We had a second crash. It's okay. It's alright. I'm not fed up. You are. Effectively, I'm kind of done anyway, at least for the purposes of this video, because all I wanted to show is that we are readily able to use static and dynamic side by side in order to make our lives for analysis a little bit easier. And again, this might not make all that much sense. I think I've gone into a little bit too much detail about registers and what to look for and how to look for it. But essentially what's going to happen is this loop is going to be completed. If I follow this now, yeah, so the loop is going to be completed. Where are we? So you can see, like, if you just pay attention to the hex at the bottom, the byte is being moved in to the 4th, and then it's going to be the 5th, and then the 6th, and then the 7th, and then the 8th, and then the 9th, and then you'll see here EX and A are not the same because it needs to be the 16th byte. I said it was the 10th. It is the 16th because I'm forgetting this is hex and this is not decimal. So 0x10 is the value, and you'd know that if you actually paid attention to what's going on here, because we know that where's the original break? The original break is here, param3, which if we go back up here, if we label this up properly, we know that param3 is 0x10. We know that param3, if UV on, which is the count, but we can't label count, because if we label count, then the whole register would change. But if we ignore the left-hand side and we just follow this, we know that UV9 is a count. We know that it is going to be the count of whatever, not the count of anything. It is just a count, and if the count is less than or equal to, it's just equal to, because less than is kind of redundant. If it's equal to 10, then there's a break, and we go into the next stage bit, which is this bit here, and which is this bit here. So we're about to, when we get there, not taken, here we go, F, not this one, there we go. EBX is 10, EDI is 10, it's then going to jump into the second bit, and we can see there's some stuff going on, it's not finished yet, so it's just going to keep going, and it's going to keep going until basically CL is 0, and that happens when there is no more data effectively. So if I'm not going to put a breakpoint here because that's only going to take me to the first loop, but if I put a breakpoint here on this second loop, then I'm able to see all of this data change and it make more sense. Now it doesn't make any sense, the data hasn't been used yet. I just know that it's going to return that data effectively. So let's see what happens now. I'm actually going to introduce a new feature of the debugger. I don't have to set a breakpoint. If I am feeling more lazy than just setting a simple breakpoint by pressing F2 or clicking the little circle, I can press F4 instead. Now F4 takes me to wherever my pointer is. So I can press F4 and it goes here. I can press F4 and it goes here. I can press F4 and it goes here. You have to be real careful with this power because it can actually lead to the destruction of your, not your malware, but it can lead to the destruction of your workflow, because you could accidentally press F4 at a place where your malware will never go. So I could accidentally do that and press F4 and it won't do anything, but I could skip over like a big function or like a big instruction that I've been looking for by accident. So just be really careful. But in this case, there's no real danger. Instead of setting a breakpoint, I'm just going to press F4 and you see all of the data change. And we can do what we've been doing and following the maths and seeing each byte incrementally move in one by one and understanding it. I think that's a really good way of just improving cognizance and knowledge about assembly language and understanding how registers work. And we'll be doing that in more detail, and I will say this channel will be focused a lot more on that side of things. But when we are just doing, I don't know, just videos about malware itself and breaking down malware from a more high level, not high level because it's still reverse engineering, but more high level than stepping into each instruction, then we won't pay so much attention to it. The whole purpose of this video was to effectively show how the debugger can work alongside Ghidra and make our analysis not just easier, but, well, readily more explainable. So we've done one function of 3. This function doesn't look like anything. It looks something to do with the process environment block, and, well, I can read, but also because I've reversed this malware a long time ago in the past. And then the third function is where the big stuff is happening, where all the main stuff is happening. And this looks terrible, but with the power of friendship, with the power of us readily, dynamically analyzing alongside static analysis, we're probably going to have a much easier time. So with that, I'm going to say this video is probably longer than it should be, but I hope we've all learned something. And if we haven't, please let me know. And I will probably next time, no I won't, this will be as live as it was last time, and hopefully we can accumulate a bunch of knowledge as we go. So cheers for watching, and I will see you hopefully in a shorter period of time than the block between the last video and this one. See you guys.